I'm ready for questions.
Okay, so any question?
I hope they are able to follow me. Starting from now is much better to read well in this. But this is the heart of the boundary. Is it how to choose a suitable operator and suitable fundamental solution. Then we leave the rest inside the domain, and then we carry out transformation of domain term to the boundary, or use Dewey reciprocity method using analog equation technique or something like that. No questions.
I may have a I think that maybe the general the questions. I think it's you may know the Professor Stern. He proposed a method which called the method MAPS, the method approximation of a particular solution.
Okay.
So that which one I think that the first the version is using the MFS plus the MPS, the method of particular solution.
Okay.
And later he I think once he told to me that because how to see that? I think that he thinks that we can remove the MFS. Then only using MPS, then can directly solve the problem.
Okay, let me tell you something.
Yeah. So maybe you know what I want to ask. Okay. So that why the but I know in the BEM because we have the integral. So yeah. So we have the which we may call the homogeneous part and also the particular solution part. So, but in the indirect formulation, so as CSC, we can remove the MFS part. So like we can remove the homogeneous solution part.
MFS is indirect form.
Yeah.
The method of fundamental solution is indirect discrete form of the boundary integral equation.
Yeah. So then I just want to ask why that one can remove the MFS part.
Okay. Yeah. First, I would like to, if you can send me this paper of MPS, this new method, I like to read it first. The second part, when we use method of fundamental solution, actually, we have to bear in our mind, for example, if we write u of x equal sigma, this is the discrete version, over k, for example, u asterisk of x and xi k times phi of xik. Actually, practically, this is, we have to know two things, 1 and 2. First of all, this is the first term in infinite series. This is the first term in infinite series. For example, what you need to add to this term is u asterisk dash of x and xik times phi d of xik. This is the intensity for the dipole. If instead of using sources, you have intensity, the derivative of the fundamental solution with respect to the source point times the intensity of the dipole plus u asterisk double dash of x and xik times the phi q of xik. This is the intensity of quadrupoles and so on until infinity. So actually you have infinite series to represent your problem. This is the first thing we need to know. But we use only the first term in the approximation. We ignore all of these terms. Okay? I have one paper for this, but I will leave it to later lecture when I talk about dipole formulation, advanced formulation. The second thing, as far as the second thing here, as far as we use only, please mute yourself. I think Muhammad Kamal.
Yeah, mute.
Mute yourself. I see. As far as we use only single term and we ignore the rest of the terms, that means this term, it works as approximation. So it works as contribution of the first term plus approximation for the rest of the terms. From this, Professor Edward Kansa got his idea about approximation using radial basis function. Instead of using the fundamental solution itself in the approximation, you can write this equation: u of x equals sigma over k f of x and xi k times phi of xi k. And this f is any radial basis function. And Professor Kansa used multi-quadric, actually, as far as you are approximating. Okay, so practically this term here, the first term of the method of fundamental solution, you can use it as contribution as the first term in the series and as approximation for the rest of the terms that you don't use them for the dipole and the quadrupole and so on. Okay, therefore we can remove this term totally. We can remove this term totally and we use particular solutions. If we use particular solutions here, so it will work as Kansa method, as a version of Kansa method. So this is my reply to your question. And it works. And the question now is how correct, how accurate is using multi-quadric, using the fundamental solution, using this. And practically we can use this inside the variational formation. And nobody have done it until now. Maybe after 6 or 7 lectures we will cover this. Okay? There is another question. One guy was talking about whether we are talking about thick plate and thick plates. The thickness is important or not. Okay. Next lecture we will have next lecture number 6, I think. We will talk about plate bending problem. I will show the contribution between Reisner plates and Kirchhoff plates. The thickness is important or not. From my opinion, there is nothing called thick plate and thin plate. This is just a description, fast description. We have thick plate and thin plate. Okay? Actually, when they derived the equation of the plates, we derived equation for plates. Okay, so we get complicated differential operator. Then we carried out 2 approximations. We'll talk about them next lecture. The first approximation, we ignored the shear deformation. The second approximation, we add derivative. We differentiated the equation. One of the equations, the shear equation, we differentiated, so we lost the information. So we ended up to nabla for the biharmonic operator applied on the deflection equal to B. Something like that. Very easy problem. Kirchhoff is the one who did that. And during these 2 approximations, the ignoring of the shear deformation, he said the plate is very thin, so he gives the name of the thin plate. We call it the thin plate theory. Coming back after Kirchhoff appeared Reisner. Reisner returned to the original plate equation. And he said, I'm not going to ignore anything. I'm going to consider all effects. But people after that, they said, as far as Kirchhoff gives the name to thin plate theory by ignoring the shear deformation, so this theory of Reisner is the thick plate theory. Actually, it is a more general theory. It is very good and very well stable. In the mathematics, the thick plate theory or the general plate theory, very well stable in mathematics. You don't need hypersingular kernels in the integral. I'm going to show you all of this. Okay, you don't need to compute hypersingular integrals because it is very annoying in simple theory. You compute hypersingular integrals, okay, and you don't need them. In fracture mechanics, forget about the simple theory. For direct, forget about simple theory. You have a lot of problems in the shear mode for fracture. You will have problems on the boundary on the shear. In finite elements, it is awful in simple theory because you ignore shear deformations. You lead to problems in the shear values inside when you have a column or something like that, or on free boundaries. You will have a lot of problems in shear deformation. Thick plate theory, you will have problems in finite element called shear locking or freezing. You will have problems, but in boundaries, you don't have this one. Okay, this is from the finite information. We will leave this to the, we'll have 2 lectures on plate bending problems. And it's very wonderful in thick plate theories, actually. It's the general plate theory, it's not thick plate theory. Okay, shall we take the rest for
Okay.
10 minutes?
Yeah. I think we have the 10 minutes rest.
Okay,
Yeah.
okay,
See you
thank
soon.
you,
Yeah.
and see you soon. And have an answer properly. Okay, thank you. Okay, we'll take the rest now. Okay,
Okay. Yeah.
okay.
Yeah.
Bye for 10 minutes.
10 minutes. Yeah.